Hey everyone. So today we're going to talk about separation of variables. What is separation of variables? It's a method for solving first-order differential equations that works pretty well in a lot of cases. I think it'll be best to work through an example while we go through the steps. So here's an example. Let's solve this equation dy dx equals xy with the initial value y of 0 is equal to 2. So the first step of this method is to move all of the terms involving x to one side and all of the terms involving y to the other side. And this includes multiplying the dx over to the right side of the equation. So when you do that, in this case, you end up with dy over y equals x times dx. Now you might say that you can't do that. Dy dx is not a fraction. You can't just multiply the dx over to the other side. What's all that about? Yeah, you're right. That's kind of sketchy. And we're going to have to go back and explain why this works later. But for now, just go with it. So the next step sort of makes things a little bit better. It says to add integral signs on both sides of the equation. This is pretty important because if you just have the equation dy over y equals x times dx, I don't even know what that means. But if you add integral signs, then it becomes something that actually means something. And that's why I like to say that you should do this step quickly before anybody notices that you wrote something down that didn't make any sense. So then the next step is to integrate on both sides. In this case, on the left, when we integrate, we get ln of y, with absolute values, of course. And then on the right, we have x squared over 2. And these are indefinite integrals, and so we need plus c's, but we can combine the plus c's from both sides into a single constant. And so we'll just put the plus c on one side. Then the next step, and this step can sometimes be hard or impossible to do, is to solve for y. In this case, we can do it by taking e to the power of both sides. But then we still have to find a way of getting rid of the absolute value sign. Now there's kind of a trick to doing that, but it's a trick that once you see it, it's pretty straightforward, so pay attention to what happens now. So the first thing is that you can rewrite e to the x squared over 2 plus c as e to the c times e to the x squared over 2. And then, since c is a constant, e to the c is a constant, and we can rewrite that with a new letter. Let's call it a. But because e to the power of anything is always positive, this a is positive. And now we can drop the absolute value sign on the left, and the corresponding thing on the right is to now allow the a to be either positive or negative. And actually, a equals 0 is also okay, but that's actually for a different reason. We sort of lost the possibility that y was equal to 0 because we divided by y. We had it in the denominator early in the solution. And so we had to go back and sort of check, is y equals 0 a solution? And yeah, it actually is. If you plug in y equals 0 into the equation, then it works. So that actually is a solution that we have to include. And then finally, the last step is to use the initial value, if it's given in the problem, to solve for the constant. So in this case, we would plug in x equals 0 and y equals 2, and then we would solve for a, and you can see that we get a is equal to 2. And then that gives us our solution to the equation. It's y equals 2 times e to the x squared over 2. And remember, you can always double check your answer by checking to see that it satisfies the initial value and that it satisfies the differential equation. So for example, I plug in x equals 0, I do get that y is equal to 2, so it satisfies the initial value. And then I can also calculate dy dx and see if it's equal to the same thing that I get if I calculate x times y. And in this case, it does work out. So this is the correct solution. So an important warning is that some differential equations are not separable, and so it's important for you to be able to know how to tell whether they are or aren't separable. And so here's an example of that. dy dx is equal to x squared plus y squared. This isn't separable because there's no way that you're going to be able to get all of the x's on one side and all of the y's on the other side. You might think, oh, I can just subtract that y squared over to the left, but you're going to have to multiply by dx at some point, and that's going to mess things up. So I encourage you to try to play around with this. Basically, what you should do is try to separate it and recognize why things go wrong. And actually, I'll tell you, in this class, separation of variables is the only technique that we're teaching you for completely solving differential equations. But even with the more advanced techniques that are out there, I don't know how to solve this equation exactly. And so this is a good example where the only recourse that's available is to use numerical methods, like Euler's method, to get approximate solutions. So then finally, I'll conclude this video with a proof that separation of variables works. You'll remember that there was this weird step where we separated the dy and the dx, which is mathematically a little bit sketchy, and so we need to kind of go back and explain why we end up getting the right answer, even though we did that thing that really we probably shouldn't have done. So the general form of a separable equation is dy dx is equal to f of x times g of y. So this just means that the right side of the equation has some function of x times some function of y. And this is separable because we can divide the function of y over to the left and then multiply the dx over to the right, and then we get everything with y on one side and everything with x on the other side. So every separable equation has this form. So then, from an equation like this, you can divide the g of y to the other side, and I'm just going to rewrite dy dx as y prime of x, just because it will provide more convenient notation for what we're about to do next. So then I can take this equation and I can integrate both sides of the equation with respect to x. This is a totally valid step because we're doing the same thing on both sides of the equation. And then, if you look at the integral on the left-hand side, you'll see that it's a good integral for making a substitution, where we rewrite the integral in terms of y instead of in terms of x. So the substitution is that y is the function y of x, and dy is y prime of x dx. And then when we make that substitution, we get an equation like this, where we have a dy integral on the left and a dx integral on the right. And this is exactly where we would be if we did separation of variables and got to that point where we wrote the integral signs on both sides. So the method of separation of variables sort of gets to the same result, but in a quicker way with fewer steps. Okay, so that's really all there is to explain. This is just one of those things that requires a lot of practice. Do a lot of problems, and you'll get the hang of it after a little while.
Bye!